All right, we're going to do a screencast on circular motion worksheet number 3, just kind of get you going on a few of the problems. I'm not going to do them for you completely. I'm just going to kind of get you going. If you have any questions, we have a office hours tomorrow, Thursday, from 9 to 10:30. So you can always ask questions then. This is the first problem on worksheet 3. It's a bi-wing aircraft. It's doing an inside loop, is what that's called. And it asks you to draw a quantitative force diagram of the forces acting on the pilot. So the pilot is your object of interest, not the plane itself, when it's upside down at the top of the loop as shown. So there's a pilot that's inside there right now, okay, inside the cockpit, and we're going to draw a force diagram of that guy. So I'm going to come over here. He's going to be my dot, and I have to draw the forces that are acting on the pilot. Obviously, I've got gravity acting down, so I'm going to just give that FG. And then at the same time, I've got the pilot is sitting on a seat that is pushing him down. At this instant, the pilot's velocity is like that. So his velocity is in that direction at that instant in time. But he's moving in a circle, right? So there has to be a force that keeps him going in that circle. So gravity is one of those things. It's one of those forces that's pointed towards the center of the circle there. But there's also the force of the seat on the pilot. I'm just going to draw it. Doesn't matter how long. I don't know if it's bigger or smaller than the gravitational force, but I'm going to call it a normal force of the seat on the pilot. So those are my two forces acting on the pilot if he's my system. All right, and both of those point towards the center of the circle. So both of those help him to go in a circle. So I've got some information here. I've got the pilot's mass. I've got the speed of the pilot, and I've got the radius of the circle that he's in at this instant as he's up here. Now, you'll notice the speed is given in kilometers per hour, so you're going to have to convert the velocity from 215 kilometers per hour into meters per second. So I'm going to let you guys do that. There's a couple conversions we need to make to get it into meters per second. So you're going to have to go from hours to seconds, kilometers into meters. So once you do that, and it's asking you to draw a quantitative force diagram, that means you have to put numbers to these forces here. And since we know the pilot's mass is 65 kilograms, that's pretty straightforward. Since we know it's m times 10 newtons per kilogram, we'll get the pilot's gravitational force very easily. We can get the net force on the pilot by doing our mv squared over r for circular motion. This part of the equation we know is the acceleration. So we'll get a number there because we know all these things. Once we convert our v into meters per second and we know the r and the m, we can calculate a number for the net force. But how do we get the normal force of the seat once we know the net force and once we know the gravitational force? Well, you have to come up with an equation for the net force based on your force diagram. The net force in this case, there's only two forces acting and they both point in the same direction. So we know the unbalanced force, or the net force, is the sum of those two. So it's going to be Fg plus the normal force of the seat on the pilot. So basically you're going to solve that for the normal force once you figure out all those numbers there. So I hope that helps you set that up. And you can use the same approach to the next problem with Tarzan. I think there's another problem with numbers on it that you'll have to do. And I'm going to go through the last problem, which is number 6. And I also want to talk about that ranking task. There's a couple ranking tasks. I just want to help you understand what you need to do for those. So let's go to that problem number 2. So this is one of the ranking tasks. It's got 6 athletes are running around the track with the same speed. That means V is the same for all. Their masses are shown as multiples of m. So for instance, this athlete B is taking this corner with a radius of 5r. He's going around the corner and he has a mass of m. This guy with 4m, his mass is 4 times B's mass. So whatever B is, let's say he's a 50 kilogram guy, A is a 200 kilogram guy. It doesn't matter what m is, it just matters the magnitude of the difference between them. Okay. First it asks us to rank the acceleration of the lettered athletes and then rank the centripetal force. The centripetal force we know is m times the centripetal acceleration And we know for something moving in a circle that centripetal acceleration is v squared over r. And all these guys are moving in a circle as they go around this corner. Okay, so this is circular motion. There's a friction force the track exerts on them that all pushes them around the circle in that direction. Okay, so you're going to rank these based on largest to smallest centripetal force, largest to smallest centripetal acceleration. So the largest centripetal acceleration, largest centripetal acceleration will be right here. The smallest will be right here. And you're going to have to figure out what the centripetal acceleration is for each one of these guys. So centripetal acceleration is not this entire expression, it's just this piece of it. Since they all have the same speed, that's not going to distinguish one guy from the other. The only thing that's going to distinguish one athlete from the other is going to be the radius of curvature of his path. And you see we've got different radii right there. You could have ties, right? You could have two people that have exactly the same centripetal acceleration at that instant. So be sure you show the ties, okay? Same down here. You could have ties for the force. So be sure to show your ties there. All right, so that's how you're going to approach the ranking task. Let's talk the last one here, which is number 6. This is a little different kind of problem. The only thing that's different about this, honestly, is the force diagram of the person that's on the ride. So you might have been on this ride actually at the St. Mary's Fair or some other similar fair where this thing spins really fast, this cylinder. It's not, tall and skinny like this. Usually they're, wider radius and they're not so deep. But it's the same idea that this thing is spinning in a circle really fast and you get thrown up against the wall because your inertia wants to keep you going in a straight line, and it's the wall of the ride that keeps you going in a circle. So that force that acts on you that keeps you going in a circle is a normal force, actually, from the wall on the ride. So you stand against the wall. So if you can picture, let's pretend we're looking at this person from the side here. We're going to model him as a dot. It's saying, so we're going to draw a force diagram in a second. Let me just read the problem to you. Kids enter the cylindrical structure when it's at rest. The floor is at point A, so you're standing on the floor as you get in. Then you stand against the wall. They usually strap you in. The ride begins to rotate really quickly. When it reaches top speed, the floor lowers to position B, and you're stuck up here. Okay, so something's keeping you suspended, even though there's no floor beneath you. So you're suspended against the floor. So if we draw a force diagram here of you, you've got the earth pulling you down. And we already said the wall, this normal force, is pushing you this way. I'm pretending I'm looking in this direction. So this is the center of the circle is over here of rotation. I'll call it the center of rotation. So like the center of the cylinder here. And then there's something holding you up. And you might remember from another problem we did earlier in the year, the thing, if you're pressed against the wall that holds you up, it has to be friction. Because you want to slide down. Your body wants to slide down because gravity's pulling you. If you're suspended, the thing that opposes motion is static friction. So we're going to call this static friction. And while you're suspended, those two are going to be equal. So the thing that causes you to go in a circle, the centripetal force, and a lot of you guys are using the term centripetal force when it asks you what's the force that keeps you moving in a circle. Centripetal force, a lot of people are putting as their answer. That's a very general term. When it asks you what the force is, you got to be really specific to the problem you're working on. In this case, that centripetal force is the normal force. Sometimes it's friction. Sometimes it's going to be the tension in a string that keeps the stopper spinning. It might be gravity that keeps the moon going in a circle, but those are examples of different kinds of centripetal forces. So you got to be really specific when it asks that question. Okay, here it says determine the period of rotation, the time for one complete cycle, necessary to keep the kids from sliding down the floor from point A to point B. To answer the question period of rotation, the first thing you have to do is solve for speed. So you first want to find V, and then remember that V is displacement over time. The time is capital T, the period for one cycle. The distance this thing travels in one cycle, in one rotation, would be the circumference. You guys all know an equation for circumference, so just figure out what the distance it travels in one rotation, what the circumference of the circle is, and knowing the velocity from circular motion, you'll be able to solve velocity once you find the unbalanced force here. Since the unbalanced force is the normal force, and that's equal to m times AC. You know what a term for AC is. Use this equation to figure out what the velocity is of the person on the ride, and then let's figure out what that period is. Okay. Hopefully you guys can do that. If you have questions, again, office hours 9 to 10 on Thursday morning. You can ask questions. Stay safe and stay close to home. Talk to you soon.